In the early 20th century, the world of physics was governed by principles that seemed both intuitive and indisputable. Classical physics, underpinned by the work of Isaac Newton, was built on the assumption that the universe operated in a highly deterministic manner. The laws of motion and the force of gravity provided a framework in which we could measure and predict the behavior of objects with great accuracy. In this framework, the behavior of objects, whether they were massive celestial bodies or everyday objects, could be understood as a predictable sequence of events. This predictability formed the foundation of classical mechanics and laid the groundwork for much of what was known about the physical world. The ability to calculate trajectories, predict the movement of planets, and even understand basic principles of energy and motion gave humanity a sense of control and certainty about the natural world. However, just as the scientific community was beginning to settle into the comfort of this deterministic worldview, a series of discoveries in the early 1900s began to challenge the status quo. One of the most revolutionary was the development of quantum mechanics, a new field of physics that sought to explain the behavior of particles on the atomic and subatomic level. It was within this framework that the work of Werner Heisenberg came into focus. Heisenberg, a young physicist working in Germany in the early 1920s, was deeply engaged in the development of quantum theory, which was rapidly gaining prominence as the next great leap in the understanding of the physical world. At the time, many of the key ideas that underpinned quantum mechanics were still being formulated, and Heisenberg's contributions would become some of the most profound and controversial in the history of science. Heisenberg's work fundamentally disrupted the principles of classical physics by introducing a concept that would later be known as the uncertainty principle. This principle, at its core, suggests that there are inherent limitations to our ability to measure certain pairs of physical properties of a particle simultaneously with absolute precision. One of the most well-known examples is the position and momentum of a particle. According to classical physics, it was always possible, in principle, to measure both the exact position and momentum of a particle. If you could measure one property, you could easily deduce the other. For example, if you knew the position of an object at a specific time, and if you knew the forces acting on it, you could calculate its future position and velocity. Heisenberg's revelation was radical in that it shattered this assumption. He proposed that the more precisely we try to measure one property, such as the position of a particle, the less precisely we can know the other property, such as its momentum. This idea was initially met with great skepticism because it ran contrary to the established belief in classical physics that everything in the universe, from the motion of planets to the behavior of atoms, could ultimately be measured and predicted with infinite precision. For centuries, the belief in the deterministic nature of physical laws had been unquestioned. If you had enough information, you could always predict the future state of any system. Heisenberg's work, however, introduced a profound level of uncertainty into this worldview. At the heart of the uncertainty principle is the idea that there is a limit to how much we can know about the quantum world. Heisenberg himself famously stated that the act of measuring a particle, particularly at the atomic or subatomic level, would inevitably disturb the system in such a way that it would make any subsequent measurements less accurate. For instance, when trying to measure the position of a particle, the very act of observing it would alter its momentum, making the measurement of that property less precise. This presented a stark contrast to the smooth, predictable world of classical physics, where measurements were assumed to be objective and independent of the observer. The implications of this discovery were far-reaching, not only in terms of physics but also in the broader philosophical context. The uncertainty principle raised profound questions about the nature of reality itself. For classical physicists, the universe was a clockwork mechanism, operating according to fixed laws. If we could only measure everything accurately, we would have full knowledge of the future. Heisenberg, however, suggested that there were fundamental limits to what we could know about the physical world. These limits were not due to any shortcomings in our measuring instruments but were an inherent feature of nature itself. The more we attempted to pin down the details of the quantum world, the more elusive they became. This concept ran counter to centuries of scientific thought and introduced a new level of uncertainty into the very fabric of physics. The impact of Heisenberg's uncertainty principle was not limited to abstract theory. It also had practical consequences for the way scientists approached experiments in quantum mechanics. The very notion that observation could alter the system being observed opened up new avenues of inquiry. Scientists could no longer assume that they could separate themselves from the physical systems they studied. This challenge to the objectivity of measurement was a significant departure from classical physics, where experiments were expected to yield repeatable and predictable results regardless of the observer. What Heisenberg introduced was a new way of thinking about the relationship between observation, measurement, and the reality of the quantum world. In classical physics, the observer was essentially a passive entity, only recording the events of the physical world. But in the quantum world, the observer became an active participant, influencing the very outcome of the experiment. This idea that the act of measurement itself could change the system being observed was a concept that had profound philosophical implications. It suggested that at the quantum level, the universe was not a fixed, predictable machine, but rather a world in which uncertainty and probability played central roles. In understanding Heisenberg's breakthrough, we also begin to realize that the concept of determinism in classical physics was based on idealized assumptions about the nature of the universe. Classical mechanics relied on the assumption that if we had complete information about a system, we could predict its future behavior with certainty. This deterministic worldview had been successful in explaining many macroscopic phenomena, from the motion of planets to the operation of everyday machines. However, at the quantum level, this certainty began to break down. Instead of a universe that could be precisely calculated, Heisenberg's work revealed a world in which uncertainty was not just an artifact of measurement but an intrinsic feature of the universe itself. The uncertainty principle raised important questions about the very nature of reality. If particles could not be precisely located, and if their momentum could not be precisely determined at the same time, then what did it mean to say that something existed in the way that classical physics defined existence? This question was further explored by other pioneers of quantum mechanics, such as Niels Bohr and Erwin Schrödinger, who contributed to the development of a new framework for understanding atomic and subatomic phenomena. However, it was Heisenberg's uncertainty principle that served as one of the cornerstones of this new, more probabilistic understanding of the universe. In essence, Heisenberg's contribution forced scientists to accept that uncertainty was a fundamental feature of the universe, one that could not be eliminated or ignored. This idea marked a radical departure from the deterministic world of classical physics and ushered in a new era of understanding. The beauty of quantum mechanics lies not in its ability to provide precise answers, but in its recognition that uncertainty is inherent in the fabric of nature itself. This acceptance of uncertainty has allowed physicists to unlock some of the deepest mysteries of the universe, leading to innovations in fields ranging from electronics to cryptography, and even our understanding of the cosmos. Heisenberg's work also opened the door to the development of quantum mechanics as a full-fledged theory. His uncertainty principle laid the groundwork for subsequent advance in quantum theory, which would eventually lead to the creation of quantum field theory, the development of quantum electrodynamics, and the formulation of the standard model of particle physics. These theories, which describe the behavior of fundamental particles and their interactions, have become the cornerstone of modern physics. In conclusion, Heisenberg's breaking of the laws of classical physics was not simply a technical achievement, it was a conceptual revolution that changed the way we think about the universe. The uncertainty principle reshaped our understanding of measurement, observation, and reality itself, challenging the long-held assumptions of classical physics. What Heisenberg gave us was not just a mathematical formula, but a new way of seeing the world, one in which uncertainty and probability were no longer seen as mere limitations but as fundamental aspects of nature. His work helped lay the foundation for the quantum revolution, and its implications continue to influence both the scientific and philosophical realms to this day. Heisenberg's uncertainty principle wasn't merely a conceptual shift in the scientific understanding of the universe. It marked a moment in history when the very nature of reality and measurement was redefined. To understand the true significance of this breakthrough, it's essential to dive deeper into The complex interplay between classical and quantum physics, the challenges that posed to established thought, and the lasting legacy of Heisenberg's work. At the heart of classical physics lay a belief in an objective reality. The universe was conceived as a machine of vast, deterministic structure that operated according to predictable laws. If you had enough information about a system, you could calculate its future behavior. Whether it was the path of a falling apple or the motion of distant planets, everything could be described with absolute precision using Newton's laws of motion and Kepler's laws of planetary motion. In this framework, it was assumed that objects existed in definite states at all times. Objects had both a position and a momentum that were fixed and measurable. This was a worldview that worked remarkably well for microscopic systems, those objects large enough for us to see, touch, and measure with the tools at our disposal. However, as science began to probe deeper into the atomic and subatomic worlds, it became apparent that this neat, deterministic view of reality didn't apply to the microscopic scale. The behavior of electrons, photons, and other subatomic particles couldn't be fully described by classical physics. Classical physics had no way to account for the strange and counterintuitive behavior observed in atomic experiments. The advent of quantum mechanics sought to explain this behavior, and Heisenberg's uncertainty principle played a key role in this shift. Before Heisenberg's groundbreaking work, scientists had assumed that the position and momentum of a particle were simply two distinct attributes that could be measured independently. For example, in the realm of classical physics, one could measure the position of a moving car, determine its speed, knowing that its velocity was simply the rate of change in its position. Similarly, one could track the trajectory of a planet moving through space and predict its future motion with great accuracy based on Newton's laws of motion and gravity. These principles were at the core of classical mechanics, and for most of human history, they explained nearly every observable phenomenon. But Heisenberg's uncertainty principle shattered that certainty. He showed that at the quantum level, the very act of measurement disturbed the system being measured. This was not a flaw in the measurement tools or methods, but an intrinsic feature of nature itself. Heisenberg's principle revealed that particles did not have definite positions or momenta until they were observed. Instead, particles existed in a state of probability, described by a mathematical function known as the wave function. This wave function provided a probability distribution, a set of possible locations and momentum. A particle might have, but it could never give an exact value for both at the same time. This realization fundamentally altered the way physicists approached the study of subatomic particles. The core idea behind Heisenberg's uncertainty principle is relatively simple. It is impossible to simultaneously measure certain pairs of properties of a particle, such as its position and momentum, with arbitrary precision. The more accurately you measure one property, the less accurate your measurement of the other will be. This limitation was not due to any shortcomings in experimental technique, but was instead a fundamental feature of the quantum world. This was a blow to the deterministic worldview that had dominated physics for centuries. In classical physics, the assumption was that the universe was fully knowable and predictable, provided that one had sufficient information. Heisenberg, however, showed that this was not the case at the quantum level. To understand why this is the case, we need to consider the role of measurement in quantum mechanics. In classical physics, measurements are assumed to be passive activities. The observer merely records the properties of the system without affecting its state. If you measure the position of a ball in motion, for example, the act of measuring does not alter the ball's position in any significant way. However, in the quantum world, the act of measurement plays an active role in determining the state of the system. The very process of measuring a particle forces it to choose a particular position or momentum. Prior to measurement, the particle exists in a superposition of all possible states, with a certain probability of being found in each state. The wave function mathematically describes this superposition, providing the probability distribution for various outcomes. When a measurement is made, the particle collapses into one of these states, and its position or momentum is determined, but the measurement itself introduces a fundamental limit to how much we can know about the system. This concept challenges the deterministic idea of an objective reality, independent of the observer. In classical physics, the universe operated like a giant clockwork machine, with all parts moving according to fixed laws. But in quantum mechanics, Heisenberg's uncertainty principle suggests that the act of observing a particle alters its state, making it impossible to know its position and momentum simultaneously with arbitrary precision. This fundamentally changes how we think about the nature of reality. If we cannot know both position and momentum with certainty, does this mean that particles do not have definite properties until we observe them? Is reality itself fundamentally indeterminate? The uncertainty principle also suggests that there is a fundamental limit to the precision with which we can predict the behavior of subatomic particles. In classical mechanics, given enough information, we could predict the future behavior of a system. If we knew the position and velocity of a ball at a given moment, we could calculate its future trajectory with high accuracy. But in quantum mechanics, the uncertainty principle makes it impossible to predict the exact behavior of a particle over time. Instead, we can only calculate probabilities. This probabilistic nature of quantum mechanics, brought to the forefront by Heisenberg, suggests that at the microscopic level, the universe is not deterministic, but governed by probabilities. This was a profound departure from the clear-cut cause and effect reasoning that classical physics had relied upon. This shift in thinking did not only have consequences for the field of physics. The implications of Heisenberg's work extended far beyond the laboratory and began to influence philosophy and the broader intellectual landscape. The uncertainty principle challenged deeply held assumptions about knowledge, reality, and determinism. For centuries, the Western worldview had been shaped by the belief that if we had enough information, we could control and predict everything around us. But Heisenberg's work revealed that there are inherent limits to human knowledge. This was a humbling realization that struck at the very heart of human inquiry and understanding. Heisenberg's uncertainty principle also laid the foundation for the development of quantum mechanics as a full-fledged theory. His work, alongside the contributions of other pioneers such as Niels Bohr, Albert Einstein, and Erwin Schrödinger, helped to create the framework for understanding the strange and counterintuitive behavior of particles at the quantum level. This new framework revolutionized the way scientists approached atomic and subatomic phenomena, leading to the development of quantum field theory and quantum electrodynamics fields that would go on to have profound practical applications in technology, medicine, and communications. Quantum mechanics has since become one of the most successful and well-tested theories in all of science, with applications in everything from semiconductors to medical imaging. Heisenberg's uncertainty principle, though a deeply unsettling idea at the time, has become a cornerstone of modern physics, shaping how we understand the behavior of matter and energy on the smallest scales. It has also reshaped our thinking about knowledge, certainty, and reality itself, ushering in a new era of scientific inquiry that continues to influence not only physics, but also other fields such as philosophy, information theory, and even the study of consciousness. In conclusion, Heisenberg's uncertainty principle was not just a theoretical breakthrough. In physics, it was a transformative idea that broke with centuries of classical thought. It challenged the very notion of a deterministic, predictable universe, suggesting that uncertainty is not just a limitation of our tools, but an intrinsic feature of nature. Heisenberg's work marked the beginning of the quantum revolution, a shift in scientific thought that continues to shape our understanding of the universe. To this day, the uncertainty principle remains one of the most profound and revolutionary ideas in the history of science, changing how we think about measurement, reality, and the very limits of human knowledge. When Heisenberg introduced the uncertainty principle, he not only challenged the foundations of classical physics, but he also reshaped the way we perceive the relationship between the observer and the system being observed. Classical physics, following in the footsteps of Newton, was grounded in a belief that the universe could be fully described by deterministic laws. These laws held that if one knew enough about a system at any given point, its future behavior could be predicted with great accuracy. Whether it was the orbit of the planets or the motion of a falling apple, classical physics implied that all objects in the universe, from the largest celestial bodies to the tiniest particles, existed in a state of definite positions and momenta. The role of the observer in this framework was passive. One could measure and record the system's properties without influencing them in any significant way. In contrast, Heisenberg's uncertainty principle suggested that the observer was no longer a passive entity in the process of scientific inquiry. Instead, the very act of measurement interfered with the system being studied, fundamentally altering its state. This is what we now refer to as the observer effect. According to classical physics, measurements were simply tools for gathering information about the external world, and they had no effect on the state of the system. However, Heisenberg's principle revealed that when measuring certain properties of particles such as their position and momentum, our very interaction with the system would cause a disturbance. This was not merely a result of experimental limitations, but a fundamental feature of the quantum world itself. The most famous example of the observer effect in quantum mechanics can be seen in the behavior of light, specifically through the concept of wave-particle duality. Light, for example, exhibits properties of both waves and particles, depending on how it is measured. When light is observed as a wave, it can interfere with itself, producing interference patterns that suggest its wave-like nature. However, when light is observed as a particle, these interference patterns disappear, and the light behaves more like a stream of individual particles, known as photons. This phenomenon, often referred to as the double-slit experiment, serves as a powerful demonstration of how the act of observation itself determines the behavior of quantum objects. The shift from wave-like behavior to particle-like behavior occurs only when a measurement is made, suggesting that the process of observation collapses the wave function, the mathematical description of all possible states of a system, into a single reality. The observer effect and the idea that measurement itself influences the outcome of an experiment raised serious philosophical questions about the nature of reality. If reality exists as a superposition of all possible states, only taking on a definite form once observed, then can we truly say that the universe exists independently of us? This question touches on deep issues of ontology and epistemology. In classical physics, the universe was seen as an objective reality, existing whether or not we observed it. In quantum mechanics, however, Heisenberg's work suggested that observation itself plays a crucial role in the formation of reality. This shift in perspective created tension not only in the field of physics but also in the broader intellectual discourse, particularly in philosophy and metaphysics. Heisenberg's uncertainty principle also raised profound questions about the limits of human knowledge. Classical physics had long been based on the assumption that with enough data, we could understand and predict the behavior of any system. The more information we had, the more certain our predictions would be. But Heisenberg's principle forced scientists to confront the uncomfortable truth that there are limits to what we can know about the quantum world. This was not due to any flaw in our measuring tools, but a fundamental feature of nature. In a sense, the universe itself became unknowable on a fundamental level. This shift in the scientific mindset was not just a technical challenge but a profound philosophical crisis. In classical mechanics, the universe was a machine and orderly system that followed predictable, deterministic laws. The relationship between cause and effect was clear. If you knew the initial conditions of a system, you could predict its future with precision. In quantum mechanics, however, Heisenberg's uncertainty principle shattered this deterministic worldview. It introduced the idea that there were inherent uncertainties in the universe, ones that could not be eliminated through better measurement or more sophisticated technology. This realization fundamentally challenged the classical ideal that the universe operated like a clockwork mechanism. In essence, Heisenberg's uncertainty principle showed that at the quantum level, particles did not have definite, well-defined properties unless they were observed. Before observation, particles existed in a state of probability, described by a mathematical function known as the wave function. The wave function gives the probability distribution of where a particle might be located, or what its momentum might be, but it cannot provide definite answers to these questions. The act of observation forces the particle to choose a particular state, collapsing the wave function into a single reality. This probabilistic nature of quantum mechanics was a sharp departure from the deterministic laws of classical physics. This new way of thinking about the nature of reality had profound implications for philosophy. The uncertainty principle introduced the idea that the universe was not fully knowable, and that uncertainty was an inherent feature of nature itself. In the classical worldview, knowledge was seen as a path to understanding and controlling the universe. The more data we gathered, the more we could control our environment. But quantum mechanics, through Heisenberg's principle, introduced a fundamental limitation on knowledge. We could never know everything with perfect certainty, especially at the quantum level. This realization created a new humility in scientific inquiry, forcing physicists to accept the inherent uncertainty of nature. In practical terms, the uncertainty principle also changed the way scientists conducted experiments. Classical experiments, in which an observer could measure a system without affecting it, were no longer possible in the quantum realm. In the quantum world, the very act of measuring a particle would alter its state. This posed new challenges for experimental design and interpretation. Scientists had to develop new tools and techniques to deal with the uncertainty introduced by observation. Quantum mechanics became not just a new set of theoretical principles, but also a new approach to experimentation and measurement. Ultimately, Heisenberg's uncertainty principle helped shape the development of quantum mechanics as a theory that was both philosophically and scientifically transformative. His work, alongside the contributions of Niels Bohr, Albert Einstein, and other pioneers of quantum theory, helped lay the foundation for our modern understanding of the atomic and subatomic worlds. The probabilistic nature of quantum mechanics, which Heisenberg's principle made clear, has since become one of the core tenets of the theory. This new understanding of reality continues to influence scientific thought today, particularly in fields like quantum computing, quantum cryptography, and quantum field theory. Heisenberg's uncertainty principle is not merely a theoretical concept, it is a fundamental feature of the universe, one that has profound implications for how we understand the natural world. By breaking with the deterministic laws of classical physics, Heisenberg showed us that the universe is far more complex, unpredictable, and mysterious than we had previously imagined. His work opened the door to a new era of scientific discovery, one that continued to reshape our understanding of reality and our place within it. The consequences of Heisenberg's uncertainty principle went far beyond the realms of theoretical physics and made a lasting impact on the way we understand the nature of reality itself. With his principle, Heisenberg broke away from the deterministic framework that had defined classical physics and ventured into the unknown territory of the probabilistic quantum world. At the heart of this revolutionary idea was a profound challenge to the notion of an objective, independent universe, a universe that operated on fixed, predictable rules that were constant across time and space. In the world Heisenberg introduced, particles could not be pinpointed with certainty. Instead, they existed in a state of probability, a cloud of possibility, that only solidified into a distinct form when an observation was made. In the context of Heisenberg's contributions, we cannot ignore the radical shift that took place in the philosophical understanding of knowledge and reality. Classical physics had embraced the belief that the world could be fully known. The laws of motion, gravity, and thermodynamics seemed to provide a comprehensive map of the physical universe. The mechanistic worldview that emerged from the Enlightenment and Newtonian physics suggested that, with enough information and the right tools, humanity could eventually explain everything about the cosmos. But Heisenberg's uncertainty principle poked holes in this belief, showing us that the universe was, in some sense, unknowable at its deepest level. In classical physics, the observer was an impartial entity, independent of the system being studied. It was as if the observer was merely a recorder, jotting down the details of the universe's workings without leaving a trace. But in quantum mechanics, the observer is an integral part of the system. The observer does not merely observe the world. The act of observation itself shapes the outcome. This realization brought about a philosophical shift of monumental proportion. If the observer is integral to the system, then reality cannot be said to exist independently of our perception of it. At the quantum level, the lines between subject and object, observer and system, blur into an intricate dance of probabilities and observations. This radical new view of the universe has deep implications for the philosophy of science and the limits of human knowledge. If Heisenberg's principle holds true, then there are fundamental limits to what we can know, not because of the limitations of our tools, but because uncertainty is an inherent feature of nature. The universe is not fully knowable, and no amount of data will ever overcome this limitation. This challenges the classical ideal that we can, in principle, know everything there is to know about the universe. Rather, it suggests that the universe is, at its core, probabilistic, and there will always be a degree of uncertainty about its behavior. In conclusion, Heisenberg's uncertainty principle was not merely a scientific breakthrough. It was a philosophical revolution that reshaped the way we understand reality. The deterministic worldview of classical physics gave way to a probabilistic understanding of the quantum world, where measurement itself plays a fundamental role in shaping the outcome. The implications of this discovery extend far beyond the realm of physics, influence our understanding of knowledge, perception, and the nature of reality itself. Heisenberg's introduction of the uncertainty principle ushered in a paradigm shift not only in physics but also in our understanding of the very nature of knowledge and reality. In classical physics, the fundamental idea was that the universe could be measured and predicted with high precision, given enough information. Determinism, the belief that every event or state of affairs is caused by preceding events according to natural laws, reigned supreme. Classical mechanics worked under the assumption that every particle in the universe, whether it was a simple rock or a complex planet, behaved in a way that was fully knowable, with a clearly defined position and velocity that could be measured. This was not just a scientific perspective, but a philosophical one, an understanding of the world as a machine that operated in predictable, orderly ways. However, when Heisenberg entered the scene, he brought with him a disruptive force that shattered this neat and tidy picture of the universe. His uncertainty principle boldly stated that there were fundamental limits to what could be known, particularly regarding the position and momentum of subatomic particles. To grasp the magnitude of this shift, it is crucial to understand that Heisenberg's revelation wasn't just a minor correction in the precision of measurement. It was a profound rethinking of the entire framework of physics itself. The implications of the uncertainty principle were immediate and profound. It revealed that the more precisely we tried to measure one property of a quantum particle, for example, its position, the less precisely we could measure another, such as its momentum. This was not due to the limitations of experimental tools, but rather an inherent property of the quantum world. The idea that particles did not have definite positions or momenta until measured was a stark contrast to the deterministic worldview of classical physics. In classical mechanics, it was assumed that particles had well-defined properties at all times, and measurement was simply the process of uncovering those properties. In the quantum realm, however, particles existed in a state of probability, with their true properties not emerging until an observation was made. This revelation caused a deep philosophical rift in the scientific community. For centuries, science had assumed that an objective reality existed independently of human observation. Whether or not we were present, the laws of physics were supposed to operate with unchanging precision. Heisenberg's uncertainty principle, however, suggested that the act of observation itself plays an integral role in shaping the outcome. The more we observe, the more we alter the system being observed. This introduced an unprecedented level of subjectivity into the process of measurement, which was in direct conflict with the classical idea that the universe is independent of human perception. To fully appreciate the magnitude of Heisenberg's discovery, we must understand the significance of this shift from determinism to probability. Classical physics, particularly through the work of Isaac Newton, held that if one knew the position and velocity of a particle, one could predict its future motion with perfect accuracy. This deterministic outlook permeated every aspect of classical mechanics, from the motion of planets to the behavior of projectiles. The universe was a vast, precise machine, and by understanding its parts, we could predict its workings. Heisenberg's uncertainty principle, in contrast, turned this certainty on its head. It suggested that at the quantum level, certainty was impossible. The future behavior of particles could not be predicted with precision, even if we knew their current state. Instead, quantum mechanics introduced the concept of probability, the idea that particles could be in multiple states at once, and only upon measurement did their properties collapse into a specific state. This idea was deeply unsettling for physicists who had grown accustomed to the deterministic framework. It introduced a degree of uncertainty into the very fabric of nature. forcing scientists to reconsider the assumptions that had guided them for centuries. In addition to the theoretical upheaval, Heisenberg's uncertainty principle had practical consequences for how experiments were conducted. In classical physics, scientists could separate themselves from the system being studied, measuring the properties of a system without influencing it in any significant way. In quantum mechanics, however, the observer became an active participant in the system. The very act of measuring altered the system, and this phenomenon had to be accounted for in experimental designs. This fundamental difference in how we approach measurement was a stark contrast to the world of classical physics, where measurements were assumed to be objective and unaffected by the observer. The implications of this new perspective were far-reaching. The notion that the act of observation could influence the outcome of an experiment led to the development of the concept of wave-particle duality. In the case of light, for example, when it was observed as a wave, it exhibited interference patterns. But when it was observed as a particle, these interference patterns disappeared, and light behaved as a stream of discrete particles or photons. This phenomenon, best demonstrated by the double-slit experiment, illustrated that the act of measurement could change the behavior of the observed system. Heisenberg's ideas not only disrupted classical physics, but also paved the way for the development of quantum mechanics. He was part of a cohort of physicists, including Niels Bohr, Albert Einstein, and Erwin Schrödinger, who collectively developed the framework that would become quantum theory. Together, they formulated a new understanding of the atomic and subatomic world, where probability, rather than certainty, governed the behavior of particles. This new framework was radically different from classical physics and Heisenberg. Uncertainty principle was a cornerstone of this revolution. The philosophical implications of Heisenberg's work were equally significant. The shift from a deterministic to a probabilistic worldview challenged not just the methods of physics but also the very nature of reality itself. Classical physics had led to a view of the universe as an orderly, predictable machine, but quantum mechanics, with its inherent uncertainties, painted a picture of a universe much stranger and less predictable. This new understanding of the cosmos led to a re-examination of the nature of reality, causality, and the limits of human knowledge. Heisenberg's uncertainty principle also had far-reaching implications for the philosophy of science. If the universe was not fully knowable, what did this mean for the scientific method? Classical physics had promised that, with enough data, we could uncover the hidden workings of nature. But quantum mechanics, particularly Heisenberg's principle, suggested that some things were simply unknowable. This was a deeply humbling realization for scientists and philosophers alike. The idea that uncertainty was an inherent feature of nature forced a rethinking of how science should proceed. Instead of aiming for perfect knowledge, scientists now had to embrace the fact that uncertainty was an unavoidable part of the process. Moreover, Heisenberg's work laid the foundation for many of the technological advancements that have since become integral to modern society. Quantum mechanics, which emerged from the principles Heisenberg helped develop, has led to breakthroughs in areas such as quantum computing, cryptography, and semiconductor technology. Devices that we take for granted today, such as smartphones, computers, and medical imaging equipment, rely on the principles of quantum mechanics. In essence, Heisenberg's uncertainty principle not only reshaped the way we think about the universe, but also helped drive the technological revolution of the 20th and 21st centuries. In conclusion, Heisenberg's uncertainty principle represents one of the most profound and transformative ideas in the history of science. It fundamentally altered our understanding of the universe, replacing the deterministic worldview of classical physics with a probabilistic view of reality. By revealing the limits of measurement and knowledge, Heisenberg forced physicists to reconsider the very nature of the universe and our place within it. His work has not only reshaped physics, but also influenced philosophy, technology, and the way we approach the mysteries of the natural world. Heisenberg's uncertainty principle wasn't merely an abstract theoretical concept. It was a fundamental challenge to the very assumptions about the nature of reality and measurement that had guided physics for centuries. At the heart of classical physics lay the belief in a deterministic universe, a universe governed by precise laws where every event and object could be fully understood and predicted with enough information. The foundation of classical mechanics, championed by figures like Isaac Newton, was based on the idea that the universe operated like a machine. If one knew the position and momentum of a particle. For instance, the future behavior of that particle could be predicted with perfect accuracy. This deterministic view of the universe had provided great success in explaining the behavior of large objects like planets and even smaller objects to a degree. However, the advent of quantum mechanics, fueled by Heisenberg's groundbreaking uncertainty principle, exposed the flaws in this worldview. In the quantum world, particles behave in ways that cannot be predicted with certainty. Instead of following predictable paths, particles exist in states of probability, described by the wave function, a mathematical function that gives the probabilities of where a particle might be found, but not its exact location until it is measured. The position and momentum of a particle are not simultaneously definable with absolute precision. Heisenberg showed that the more precisely one tries to measure the position of a particle, the less precisely one can know its momentum, and vice versa. This principle, which introduced inherent limitations to our ability to measure certain properties of quantum particles, was revolutionary in its implication. The uncertainty principle radically challenged the classical view of science, where it was assumed that, with enough data, we could describe and predict any phenomenon in the universe. Heisenberg's insight forced a rethinking of the very methods of scientific inquiry. The notion of absolute certainty, so central to classical physics, gave way to the idea of probability and uncertainty. In essence, Heisenberg showed that, at the atomic and subatomic levels, the universe didn't work like a machine with predictable, clockwork precision. Instead, it operated with a fundamental indeterminacy, where certain outcomes were not just unknown, they were unknowable. The realization had deep philosophical implications, suggesting that the universe may not be a deterministic system but one shaped by probabilities, where certainty is elusive. This uncertainty was not just a technical limitation, but a characteristic of the quantum world itself. The act of measurement, Heisenberg argued, disturbs the system being observed. In classical physics, it was assumed that measuring the position of an object, for instance, would not affect its state. But in quantum mechanics, the very act of measuring a particle changes its state in unpredictable ways. This was not a consequence of poor measurement techniques or faulty instruments, but a fundamental feature of quantum systems. Heisenberg's uncertainty principle thus opened up a new way of thinking about observation and reality. It suggested that the observer was not a neutral participant in the process of measurement, but an active agent whose interactions with the system could alter the system itself. In classical mechanics, scientists sought to describe the universe in terms of precise quantities. If we knew the position and velocity of a particle, we could calculate its future behavior. But in the quantum world, particles are described by probability distributions rather than definitive values. The wave function, which represents these probabilities, can give the likelihood of finding a particle in a particular location or with a certain momentum, but it cannot provide a definitive answer about both properties simultaneously. This means that, at the quantum level, our knowledge of the universe is limited not by the tools at our disposal, but by the very nature of the particles themselves. This was a shocking revelation that shook the foundations of physics. The uncertainty principle also had profound implications for the philosophy of science and our understanding of knowledge. Classical physics had embraced the idea that the universe could be fully known, that if we had enough information, we could predict the future with great accuracy. This belief in a fully knowable universe underpinned much of the scientific revolution and Enlightenment thinking. Heisenberg's principle, however, suggested that there were fundamental limits to what we could know about the universe, particularly at the quantum level. This realization raised profound questions about the nature of knowledge itself. If some aspects of the universe were fundamentally unknowable, what did this mean for the limits of human understanding? Could we ever truly know the world in the way we had hoped? Heisenberg's uncertainty principle thus undermined the classical notion of an objective, observer-independent reality. In classical physics, the universe was thought to exist in a state that was independent of our perception of it. But in quantum mechanics, the observer was shown to play an active role in determining the state of a system. The very act of observation forces particles into definite states. This was not just a philosophical challenge to our understanding of the universe, but a practical one as well. The observer effect, the idea that the act of measurement alters the system being observed, became central to quantum theory, and it led to new ways of thinking about experimental design and interpretation. For example, in the famous double-slit experiment, particles like electrons or photons are fired at a barrier with two slits. When not observed, the particles pass through both slits simultaneously and interfere with themselves, creating an interference pattern. This pattern suggests that the particles are behaving like waves, existing in a superposition of all possible paths. However, when the particles are observed when a measurement is made to determine which slit they passed through, the interference pattern disappears and the particles behave as if they are individual particles, passing through one slit or the other. The act of measurement collapses the wave function and forces the particle to adopt a definite state. This phenomenon, observed countless times in laboratory experiments, highlights the central role that observation plays in quantum mechanics. This strange and counterintuitive behavior of particles led to a re-evaluation of the nature of reality itself. If particles exist in a superposition of multiple states until observed, what does this mean for the idea of an objective reality? In the classical worldview, reality was considered to be independent of human perception, existing in a state of certainty, whether we observed it or not. But in the quantum world, reality appears to be fluid, dependent on the act of observation. This raised profound questions about the nature of existence and the role of consciousness in shaping the world around us. One of the key philosophical implications of the uncertainty principle was its challenge to the idea of a deterministic universe. In classical physics, it was assumed that if we had complete knowledge of a system, we could predict its future behavior with certainty. However, Heisenberg's uncertainty principle showed that this was not possible in the quantum world. The future behavior of quantum particles could not be predicted with certainty, no matter how much information we had about their current state. Instead, quantum mechanics provided only probabilistic predictions, where the exact outcome of an event could not be determined, only the likelihood of various outcomes. This shift from determinism to probability had far-reaching implications beyond physics. It called into question the very nature of causality, free will, and even the concept of time itself. If the universe was not fully predictable, what did this mean for our understanding of cause and effect? How did this uncertainty affect our beliefs about human agency and the possibility of free will? These questions extended the reach of quantum mechanics into realms beyond science, influencing philosophy, psychology, and even theology. The practical applications of Heisenberg's uncertainty principle, though initially theoretical, have had profound impacts on modern technology. Quantum mechanics, which arose from Heisenberg's work and that of his contemporary, has led to the development of technologies that have transformed our world. Quantum computing, which relies on the principles of superposition and entanglement, promises to revolutionize computing by performing calculations that were previously thought to be impossible. Quantum cryptography, which uses the principles of quantum mechanics to create unbreakable encryption, is already changing the way we think about security in the digital age. Additionally, technologies like MRI scanners, which rely on principles of quantum mechanics, have become indispensable tools in medicine. In conclusion, Heisenberg's uncertainty principle not only transformed the way scientists approach the study of particles, but it also changed our fundamental understanding of the universe. The shift from a deterministic worldview to a probabilistic one marked a turning point in the history of science, forcing us to rethink our assumptions about knowledge, reality, and the role of observation in shaping the world. Heisenberg's work continues to resonate through modern physics, philosophy, and technology, offering a new lens through which we can understand the complex and uncertain nature of the universe. The legacy of the uncertainty principle is one of profound change, shifting our perspective from certainty to probability, from determinism to indeterminacy, and from an objective universe to one shaped by the very act of observation. The uncertainty principle, introduced by Werner Heisenberg, not only upended our understanding of the atomic and subatomic worlds, but also began to challenge fundamental assumptions about reality, observation, and knowledge itself. In classical physics, the universe was often viewed as a machine governed by deterministic laws. If we had complete information about a system's initial conditions, we could predict its future with perfect accuracy. This view was embraced by the likes of Isaac Newton, whose laws of motion and universal gravitation were the bedrock of classical mechanics. This vision of a clockwork universe where every movement could be predicted provided humans with a sense of mastery over nature, laying the foundation for the rise of modern science and technology. However, as Heisenberg's uncertainty principle was introduced and developed further, this long-held understanding began to unravel. At its core, the uncertainty principle reveals that there are limits to how precisely certain pairs of properties of particles, such as their position and momentum, can be known simultaneously. More specifically, Heisenberg's work showed that the more accurately we measure one of these properties, the less precisely we can measure the other. This was a radical shift from classical physics, where the belief was that all particles, whether large objects or tiny subatomic ones, could be described with exact numbers. Heisenberg's principle exposed a fundamental gap in our knowledge, revealing that at the quantum level, the world operates with inherent uncertainties that cannot be eliminated or reduced. This realization had profound consequences, not only for the field of physics, but also for our broader understanding of the universe. The idea that measurement could disturb the system being measured was a critical departure from classical mechanics. In classical physics, the observer was seen as a passive entity, merely recording the properties of a system without influencing its state. In quantum mechanics, however, the observer was revealed to play an active role in shaping the state of the system. Heisenberg's uncertainty principle placed observation at the center of quantum mechanics and highlighted how measurement itself could alter the reality being studied. This fundamental shift in how we think about the relationship between observer and system led to a rethinking of the very nature of reality itself. The uncertainty principle, by introducing limits to what can be known, forced physicists to rethink the way they approached experiments. In classical physics, an observer could measure the properties of a system without affecting it in any significant way. The systems studied were assumed to have well-defined properties independent of the observer. But in the quantum realm, the act of measurement introduces a disturbance in the system, causing it to behave differently than it would without observation. This idea was difficult to accept for many physicists who had long been accustomed to the belief that the universe was objective and independent of human perception. With Heisenberg's discovery, however, it became clear that at the quantum level, the very act of measuring could alter the course of events. This new understanding introduced a level of subjectivity into the scientific process. If the act of measurement itself plays a crucial role in determining the state of a system, then the universe was no longer something external and independent from us. Instead, it was revealed that reality was entangled with the observer in a way that had not been previously understood. This idea of entanglement, where particles can exist in states that are only defined when they are observed, directly challenged the classical concept of an objective universe that exists regardless of human observation. This shift in understanding also had deep implications for the way we think about knowledge. Heisenberg's uncertainty principle suggested that there were limits to our ability to know the world, and these limits were not simply due to our technological shortcomings, but were intrinsic features of the quantum world itself. Heisenberg's principle brought forth the concept of probability as the core of quantum mechanics. Rather than a deterministic universe where every event was predictable, quantum mechanics introduced a probabilistic framework in which particles existed in a state of superposition, with various potential outcomes. The wave function, a mathematical tool used to describe these superpositions, provided the likelihood of where a particle might be located or what momentum it might have, but it could not provide a definitive answer until a measurement was made. This shift from determinism to probability created a fundamentally different approach to understanding the universe. In classical mechanics, the universe was like a giant machine, its gears and wheels turning in precise harmony. In quantum mechanics, the universe became a sea of probabilities, where the outcome of events could never be predicted with certainty. This probabilistic view of the universe had a profound impact on how physicists understood cause and effect. In classical mechanics, one could trace a clear chain of events, where the cause directly led to an effect. If we knew the initial conditions of a system, we could determine its future behavior with accuracy. But in quantum mechanics, the exact outcome of an event could never be known with certainty. Instead of deterministic cause and effect relationships, quantum mechanics provided probabilities for different outcomes, allowing scientists to make statistical predictions rather than precise determination. This shift had deep philosophical consequences, as it raised questions about the very nature of causality and the role of free will. If the universe operates probabilistically, then how much control do we truly have over our actions? Are our choices simply the product of chance? Or is there still room for free will within this probabilistic framework? The philosophical implications of Heisenberg's uncertainty principle were not just limited to questions about determinism and free will, but extended to broader concerns about the nature of knowledge and reality. Classical physics had long been based on the assumption that the universe was knowable, and that, with enough data, we could understand its underlying laws. This view had been the foundation of the scientific revolution and the Enlightenment, where reason and observation were seen as the tools to unlock the mysteries of the natural world. However, Heisenberg's discovery forced us to confront the possibility that some aspects of the universe might forever remain beyond our reach. The inherent uncertainty in quantum mechanics suggested that there were limits to what we could know, not just because of our current technological limitations, but because of the nature of the universe itself. This introduced a level of humility into the scientific enterprise, reminding scientists that there will always be aspects of reality that are beyond our comprehension. While the philosophical questions raised by Heisenberg's uncertainty principle were profound, the practical consequences were equally significant. In the decades following its introduction, the principles of quantum mechanics, including the uncertainty principle, formed the foundation for the development of modern technology. Quantum mechanics led to the invention of the transistor, which revolutionized computing, and the development of lasers, which have applications in everything from telecommunications to medicine. Quantum mechanics also enabled the field of quantum computing, which promises to usher in a new era of computation, where calculations that would take traditional computers millennia to complete could be performed in mere seconds. Furthermore, quantum cryptography, based on the principles of quantum mechanics, has the potential to create unbreakable encryption methods, changing the way we secure information in the digital age. The influence of Heisenberg's work can also be seen in the field of modern medicine. Technologies such as magnetic resonance imaging (MRI) rely on quantum principles to provide doctors with detailed images of the inside of the body. The field of quantum biology is exploring how quantum mechanics may play a role in biological processes such as photosynthesis, and even the way birds navigate using Earth's magnetic field. These breakthroughs would not have been possible without the foundational work laid by Heisenberg and other pioneers of quantum mechanics. In conclusion, Heisenberg's uncertainty principle shattered the classical worldview, replacing determinism with probability and challenging our assumptions about the nature of the universe. The principle introduced a new framework for understanding the atomic and subatomic worlds, where measurement itself plays a crucial role in shaping reality. The consequences of this discovery were profound, not only for physics, but also for our understanding of knowledge, causality, and free will. Heisenberg's work opened the door to a new era of scientific exploration and technological innovation, the impact of which continues to shape the world today. The uncertainty principle remains one of the most important and enduring contributions to modern physics, influencing everything from quantum computing to cryptography and medicine. Heisenberg's uncertainty principle introduced a profound shift in the world of physics, challenging the long-standing assumptions of determinism that had shaped classical mechanics for centuries. One of the most significant outcomes of Heisenberg's work was the realization that the act of measurement could never be perfectly precise. In classical physics, the notion was that with enough information, scientists could predict the future behavior of a system with complete certainty. This idea was rooted in the belief that the universe, at its most basic level, operated like a machine, its every part functioning according to deterministic laws. The movement of objects, whether large or small, could be calculated and predicted precisely if the proper data was available. However, Heisenberg's principle shattered this view by revealing that, at the quantum level, some aspects of reality are inherently uncertain. Heisenberg's uncertainty principle asserts that it is impossible to simultaneously measure both the position and momentum of a particle with perfect accuracy. The more precisely one measures the position of a particle, the less precisely its momentum can be known, and vice versa. This principle was not just a theoretical observation, but a fundamental property of quantum systems. The uncertainty was not due to the limitations of our measurement tools. Rather, it was a natural feature of the quantum world. In classical physics, it was assumed that every particle in the universe had a definite position and velocity at any given time, and these could be measured with sufficient precision. But in the quantum realm, the position and momentum of particles exist in a state of probability rather than certainty until observed. This uncertainty in measurement also led to the introduction of a new view of the observer's role in scientific inquiry. In classical mechanics, the observer was considered a passive participant. The observer could measure and record the properties of a system without affecting its state. However, in quantum mechanics, the observer was shown to play an active role in determining the outcome of the measurement. The very act of observing a particle, whether it is measuring its position or momentum, disturbs the system, altering the particle's state. This is a crucial departure from classical physics, where measurement was assumed to be an impartial, non-intrusive process. In the quantum world, the observer and the observed are intricately linked, and measurement itself becomes an integral part of the system. One of the most striking implications of the uncertainty principle was its challenge to the idea of an objective reality. Classical physics had been rooted in the belief that the universe existed independently of human perception. The laws of nature operated the same way, regardless of whether or not we observed them. However, in the quantum realm, Heisenberg's principle suggested that reality is not objective in the traditional sense. Instead, the act of observation determines the state of the system. Particles do not have definitive properties until measured. This raised deep philosophical questions about the nature of reality. If particles do not exist in definite states until observed, does that mean reality is shaped by human perception? Can the universe be said to exist in the same way when it's not being observed? These questions challenged the classical view of an external, objective reality, and pushed scientists to reconsider the nature of existence itself. Moreover, the uncertainty principle led to the emergence of probabilistic, rather than deterministic models of the universe. Classical mechanics had been based on the assumption that, given sufficient information about the present state of a system, its future behavior could be predicted with certainty. If we knew the position and velocity of a ball, we could predict where it would go next. But in quantum mechanics, the future behavior of particles cannot be predicted with certainty. Instead, the best we can do is calculate the probability of various outcomes. The wave function, a central concept in quantum mechanics, describes these probabilities. When we measure a particle, its wave function collapses, and it assumes a specific position or momentum. Before measurement, however, the particle exists in a superposition of all possible states. This probabilistic nature of quantum mechanics stands in stark contrast to the deterministic laws of classical physics fundamentally alter how we think about causality and the predictability of the universe. In conclusion, Heisenberg's uncertainty principle revolutionized physics by revealing that some aspects of the quantum world are inherently uncertain, challenging the classical worldview that assumed a deterministic universe. The principle showed that the more precisely we measure one property of a particle, the less precisely we can know another, highlighting the limits of human knowledge. It also introduced the idea that observation itself plays a crucial role in shaping reality, blurring the line between the observer and the observed. This shift from determinism to probability in quantum mechanics raised profound questions about the nature of reality, knowledge, and existence. As a result, Heisenberg's work laid the groundwork for the development of modern quantum mechanics and had lasting philosophical and scientific implications. Heisenberg's uncertainty principle introduced a paradigm shift in our understanding of the universe, dismantling centuries of classical physics assumptions. The core concept of the uncertainty principle lies in the idea that certain properties of particles, such as position and momentum, cannot both be measured with absolute precision simultaneously. This marked a departure from classical physics, where the expectation was that all particles had definite positions and velocities, and, with enough information, their future states could be predicted precisely. Heisenberg's theory introduced the radical idea that, on the quantum scale, the more accurately one measures a particle's position, the less accurately one can measure its momentum and vice versa. This challenge to classical thinking opened the door to a new era in physics where uncertainty is no longer a limitation, but an inherent characteristic of nature itself. Classical mechanics had always assumed that the universe operated in a deterministic fashion, where if we had enough data about a system, we could predict its future state with precision. Newton's laws of motion worked on this principle, where every action had a predictable reaction, and the motion of every object could be determined if its initial conditions were known. Heisenberg's uncertainty principle shattered this certainty by asserting that, at the quantum level, no matter how much information we gather, we can never know both the position and momentum of a particle with perfect accuracy. Instead of a predictable, clockwork universe, Heisenberg's principle revealed a probabilistic universe where outcomes could only be described in terms of probabilities. The principle also introduced the concept of wave-particle duality, a phenomenon observed in particles like photons and electrons. According to classical physics, objects could either be considered waves or particles, but Heisenberg's work suggested that particles, at the quantum level, could exhibit properties of both. This dual nature of particles was a departure from the classical notion of definite, observable properties. When observed, particles seem to collapse into a definite state, either behaving as particles or as waves, depending on how the measurement is made. This was evident in experiments like the double-slit experiment, where light, when not measured, produces an interference pattern, showing its wave-like nature, but when measured, it behaves as a particle. This observation showed that the state of a quantum system could be influenced by the act of measurement itself, leading to a rethinking of the role of the observer in the universe. Another crucial aspect of Heisenberg's uncertainty principle is its challenge to the concept of objectivity in measurement. Classical physics had always assumed that measurements were objective and independent of the observer. This idea was rooted in the belief that the universe existed in a definite state, independent of whether we observed it. However, Heisenberg demonstrated that, in the quantum world, the act of observation itself influences the outcome. The observer is no longer a passive recorder of reality, but an active participant in determining the state of the system. The uncertainty principle suggests that reality is not fixed, but is shaped by our measurement, fundamentally altering the relationship between the observer and the system. Heisenberg's work also led to a shift in the philosophical understanding of reality itself. The uncertainty principle emphasized the inherent limitations in our ability to know the universe, marking a departure from the classical notion that all knowledge is achievable with enough data. Classical physics held that, with sufficient information, we could understand and predict every system, from the motion of planets to the behavior of atoms. But the quantum world, as revealed by Heisenberg, was not only probabilistic but fundamentally uncertain. This shift raised important questions about the nature of knowledge, suggesting that some aspects of reality may forever remain unknowable. It also challenged the philosophical idea of determinism, the belief that every event is caused by preceding events in a chain of cause and effect. In the quantum world, Heisenberg's principle suggested that the universe is not fully determined, but is instead governed by probabilities. Finally, Heisenberg's uncertainty principle had far-reaching consequences for the development of quantum mechanics and modern technology. The principle led to the development of quantum field theory, which describes how particles interact through fields, and the Standard Model of Particle Physics, which is a framework that explains the fundamental forces of nature. These advancements in theoretical physics have had profound practical applications. For instance, quantum mechanics has played a crucial role in the development of technologies like semiconductors, lasers, and MRI machines. The principle also laid the groundwork for the emerging field of quantum computing, which promises to revolutionize computing by performing calculations that are currently impossible for classical computers to achieve. Quantum cryptography, based on the principles of quantum mechanics, also holds the potential to create unbreakable encryption methods, securing digital information in unprecedented ways. In conclusion, Heisenberg's uncertainty principle did more than challenge established physics. It fundamentally changed how we view the universe. It introduced the idea that, at the quantum level, certainty is unattainable, and replaced the deterministic worldview with a probabilistic one. This shift had profound implications not only for physics but for our understanding of knowledge, reality, and the role of the observer. The principle not only reshaped theoretical physics but also contributed to the development of technologies that have transformed the modern world. Heisenberg's work continues to influence science, philosophy, and technology. marking one of the most important breakthroughs in the history of physics. Heisenberg's uncertainty principle was one of the most groundbreaking ideas to emerge from the early days of quantum mechanics. It marked a decisive break from the principles of classical physics, which held that the universe operated predictably and deterministically. Classical mechanics, based on the laws established by Isaac Newton, assumed that if we knew the position and velocity of an object, we could predict its future motion with absolute certainty. Heisenberg's uncertainty principle, however, introduced the radical idea that, at the quantum level, this is no longer true. The principle suggests that there are fundamental limits to how precisely we can know both the position and the momentum of a particle at the same time. The more accurately we measure one, the less accurately we can measure the other. This fundamental uncertainty exists not due to our lack of measurement tools, but because it is an inherent feature of nature itself. At the heart of the uncertainty principle is the idea that quantum particles do not have well-defined positions or momenta until they are measured. In classical physics, we assumed that objects existed in a definite state regardless of observation. If you know the position and speed of a ball, for example, you can calculate its future trajectory. But in the quantum world, particles such as electrons exist in a state of probability until we measure them. They do not occupy a single, definite location or possess a precise momentum until they are observed. Before measurement, quantum particles exist in a cloud of possible states, which is described by a mathematical function known as the wave function. The wave function gives the probabilities of where a particle might be or what its momentum could be, but it does not provide a definitive answer. This brings us to another key implication of Heisenberg's principle, the relationship between measurement and reality. In classical physics, measurements were considered passive activities. The observer was assumed to have no influence on the system being observed. However, in the quantum world, the act of measurement plays a crucial role in shaping the outcome. When we measure the position of a particle, for example, we force it to choose a specific location, collapsing its wave function. Before the measurement, the particle's location was not defined but existed in a superposition of all possible locations. The very process of observation alters the system, making it clear that the observer and the observed are not separate entities, but are intricately linked. This concept challenges the classical notion of objectivity, suggesting that the reality we observe is inextricably tied to the act of observation itself. The uncertainty principle also posed a significant philosophical challenge to classical concepts of determinism. Classical physics operated on the assumption that the universe was predictable and deterministic. If you knew the initial conditions of a system, you could calculate its future behavior. In other words, the future was determined by the present, and with enough information, the future could be predicted with perfect accuracy. But Heisenberg's uncertainty principle suggested that the future of quantum particles cannot be predicted with certainty. Instead of a deterministic universe, quantum mechanics offers a probabilistic model where the exact outcome of an event cannot be known, only the likelihood of different possibilities. This shift from a deterministic view to a probabilistic one was one of the most significant changes in our understanding of the physical world. This probabilistic nature of quantum mechanics led to further philosophical debates about the nature of reality itself. If we cannot know both the position and momentum of a particle with certainty, then can we ever truly know the world as it is? Classical physics relied on the assumption that reality existed independently of our perception of it, that the universe operated according to fixed, objective laws. But the uncertainty principle introduced a new perspective. Reality, at the quantum level, is not fixed. It is shaped by the act of measurement, and until we measure it, we cannot know it. This suggests that the universe may not be as objective as we once believed, but rather, it may be subjective, influenced by the observer in ways we had never imagined. This opens up profound philosophical questions about the nature of existence and our place in the universe. The uncertainty principle also introduced a new approach to scientific experimentation. In classical mechanics, the goal was to make measurements as precise as possible in order to predict the behavior of a system. But in the quantum world, the very act of measurement disturbs the system, and this disturbance must be taken into account when designing experiments. This led to new techniques and ways of thinking about experimentation as scientists could no longer rely on the assumption that measurements could be made without affecting the system. This also meant that scientists had to deal with the inherent uncertainties in their results, accepting that some level of indeterminacy would always remain, even with the most sophisticated tools. Lastly, Heisenberg's uncertainty principle laid the foundation for many of the developments in modern quantum physics. It was a central concept in the development of quantum mechanics and contributed to the creation of quantum field theory, which describes the interactions between particles and fields. The principle also influenced the development of quantum electrodynamics, which is the theory of how light and matter interact, and the standard model of particle physics, which is the most successful theory to date describing the fundamental particles and forces of nature. These advances have led to groundbreaking technological development in fields such as semiconductors, lasers, and medical imaging. Quantum mechanics, which grew out of the work of Heisenberg and his contemporaries, has become the foundation of much of the technology that drives our modern world. In conclusion, Heisenberg's uncertainty principle was a revolutionary idea that fundamentally altered our understanding of the physical world. It challenged the deterministic worldview of classical physics and introduced a probabilistic framework for understanding the behavior of quantum particles. The principle highlighted the inherent limitations in our ability to measure certain properties of particles simultaneously and emphasized the role of the observer in shaping reality. It also raised profound philosophical questions about the nature of knowledge, existence, and the universe itself. Finally, the uncertainty principle laid the groundwork for the development of modern quantum mechanics, which has had a lasting impact on both science and technology. Heisenberg's work continues to shape our understanding of the universe and our place in it, making his contribution one of the most important in the history of physics. Heisenberg's uncertainty principle is one of the most profound and influential ideas to emerge in the 20th century. It shook the foundations of classical physics and redefined our understanding of the microscopic world. Classical physics had long been governed by the notion of determinism, the belief that, with enough information, we could predict the future with complete certainty. This view was built on the works of Isaac Newton, whose laws of motion were able to predict the behavior of large objects with great precision. Classical physics relied on the assumption that particles and objects in the universe had definite positions and velocities at any given time. But Heisenberg's uncertainty principle challenged this certainty, showing that at the atomic and subatomic levels, such precision is unattainable. The core of Heisenberg's uncertainty principle lies in the relationship between position and momentum. According to this principle, it is impossible to simultaneously measure both the position and momentum of a particle with perfect precision. The more accurately one measures the position of a particle, the less accurately one can measure its momentum, and vice versa. This is not due to limitations in our measuring instruments, but rather a fundamental feature of nature itself. This marked a radical departure from classical physics, where the belief was that particles and objects could be observed with arbitrary precision, allowing us to predict their future behavior with certainty. Heisenberg's principle showed that this idea was incompatible with the way quantum particles behave. One of the significant implications of the uncertainty principle is the concept of wave-particle duality. In classical physics, particles were treated as distinct individual objects, while waves were considered different phenomena altogether. However, Heisenberg's work helped uncover the fact that at the quantum level, particles like electrons can behave both as particles and as waves, depending on how they are observed. This wave-particle duality is a fundamental feature of quantum mechanics and highlights the complexity and strangeness of the quantum world. The uncertainty principle ties into this by suggesting that the exact behavior of a quantum particle cannot be fully known, as its nature is both probabilistic and dependent on how it is observed. This dual nature of particles is most famously demonstrated through the double-slit experiment. When particles such as electrons are sent through two slits, they create an interference pattern typical of waves. However, when the particles are observed or measured at the slits, they behave as particles, and the interference pattern disappears. This shows that the very act of observation influences the system, collapsing the wave function and forcing the particle to take a definite position. Heisenberg's uncertainty principle is closely related to this phenomenon as it underscores the idea that observation itself plays a critical role in determining the state of a quantum system. The observer is no longer a passive participant, but an active one that shapes the reality being studied. The uncertainty principle also challenges the concept of an objective reality. In classical mechanics, it was assumed that the universe exists independently of the observer. Whether we observe it or not, the laws of physics govern the behavior of particles in an objective, fixed way. However, Heisenberg's principle suggests that at the quantum level, particles do not have well-defined properties until they are measured. Before observation, particles exist in a superposition of multiple possibilities. This suggests that reality, at the quantum scale, is not objective but rather subjective, shaped by the act of observation. This idea challenges the classical notion that reality is external and independent of the observer, offering a more complex and entangled relationship between the observer and the observed. Another important implication of the uncertainty principle is the role of probability in quantum mechanics. Unlike classical physics, where the behavior of particles can be predicted with certainty if the system is known, quantum mechanics is inherently probabilistic. The uncertainty principle underscores this probabilistic nature by showing that we cannot predict both the position and momentum of a particle with certainty, only the probability of where it might be and what its momentum might be. The wave function, which is central to quantum mechanics, describes these probabilities, allowing us to calculate the likelihood of finding a particle in a particular location or with a certain momentum. This shift from determinism to probability was one of the most revolutionary aspects of quantum theory and signified a new way of understanding the universe. The uncertainty principle also raised profound philosophical questions about the limits of human knowledge. Classical physics had been based on the assumption that, with enough data, we could fully understand the universe. Scientists believed that by measuring the properties of particles and objects, they could eventually uncover all the mysteries of nature. However, Heisenberg's principle introduced a fundamental limit to this knowledge, showing that some aspects of reality are inherently unknowable. This realization was not just a technical challenge for physicists. It forced a rethinking of how we approach knowledge itself. If some things are unknowable, what does this mean for our understanding of the universe and our place in it? This question has reverberated throughout philosophy, as it challenges the classical ideal of complete knowledge. Finally, Heisenberg's uncertainty principle had far-reaching consequences for technology. The principles of quantum mechanics that emerged from Heisenberg's work laid the foundation for numerous technological advancements. Quantum mechanics has led to the development of semiconductors, layers, and technologies such as MRI scanners. These applications have revolutionized fields like computing, telecommunications, and medicine. Quantum mechanics also paved the way for the development of quantum computing, which has the potential to solve problems that are currently intractable for classical computers. Quantum cryptography, which uses quantum principles to secure information, promises to create communication systems that are virtually immune to eavesdropping. These advancements show how Heisenberg's principle, while originally a theoretical concept, has had profound practical implications that continue to shape modern technology. In conclusion, Heisenberg's uncertainty principle fundamentally changed our understanding of the universe. It introduced the idea that the quantum world operates with inherent uncertainty, challenging the deterministic view of classical physics. It revealed that measurement itself plays a crucial role in shaping the state of a quantum system, and that reality, at the quantum level, is influenced by the observer. This principle also raised important questions about the nature of knowledge, suggesting that there are limits to what we can know. Lastly, Heisenberg's work contributed to the development of quantum mechanics, a field that has revolutionized science and technology, with applications in fields ranging from computing to medicine. Heisenberg's uncertainty principle continues to shape our understanding of the quantum world and the very nature of reality itself.